Okay, as a little bit of warm-up here for section 2.6, we're going to graph what we call a rational function. So class is graphing right now, and we're going to make sure that we include parentheses around the numerator and the denominator. Record this. If you're using a TI-83, does it look like your branches are connected to each other? Okay, it does. That's because TI-83s are older and they have to connect these parts to make them continuous. But hopefully what you can see here is we've got a vertical asymptote line at -2 and another vertical asymptote line at +2. Why would we have vertical asymptote lines at 2 and -2? Mr. Dillevin? I'm sorry, I couldn't hear your response. Why do we have vertical asymptotes at 2 and -2?
Because it makes the equation 0.
You're right, it makes the denominator 0. Very good, Jack. We'll record that. Any horizontal asymptotes? No? Well, in a way there is, if we consider the outside parts of the graph. Looking way out here, what are my y values getting very, very close to? 0. What are my y values getting very, very close to way out here? 0 as well. So we're going to introduce a little bit later what we call a horizontal asymptote to describe the end behavior. Okay, we're moving on to example number 3 now, and we're going to look at, again, finding some more asymptotes, both horizontal and vertical. And our function, f of x, is a rational function. And let's get a quick review on what it means to be a rational function. A rational function has some sort of a variable in a denominator, which we clearly have here. Looking at a graph, screenshot on the right-hand side, well, I would ask you guys out here in the crowd, probably Allison knows the answer to this. Where is there a vertical asymptote?
There isn't one.
Very good, Allison. Why isn't there a vertical asymptote? Can anybody else figure out why? So Allison says there are no vertical asymptotes. Anybody know why? Harold?
Because it's impossible to have the denominator be 0.
Awesome, correct, good answer. Do you guys see a horizontal asymptote anywhere on the graph? Mr. Corser, where's their horizontal asymptote?
There's a horizontal asymptote at 1.
Why do you think there's one at 1?
I think that because degrees are the same on both the top and bottom.
Okay, they're both squared, so they're both second degree.
Yep, and you would divide the leading coefficients by themselves.
Well, I don't see a leading coefficient in front of the x squared.
It's always 1.
It's 1. What's the leading coefficient then for the x squared in the denominator?
1 as well.
1 as well. So if we divide 1 by 1, we get?
1.
Awesome. So uncovering this little box right here, we talked about why there are no vertical asymptotes. That's because the denominator cannot be 0, and there's a horizontal asymptote at 1, thanks to Mr. Corser, because the leading coefficients divide into 1. Now, we're going to look at 3 more functions down here. So we're going to right now have you guys in class graph g of x, the first. Okay, having graphed our new function, 5x squared plus 2, over the quantity x squared plus 2, we get this graph. Does there appear to be a vertical asymptote? Jack?
No.
Okay, we're now looking at another function. This has changed up a little bit. Our numerator is 5x plus 2. Our denominator is x squared minus 9. This is again rational because it's got a variable in the denominator. And we see what appears to be places for vertical asymptotes. Where might those vertical asymptotes occur?
3 and -3.
How come algebraically would they be at 3 and -3?
When you square 9 or square root 9.
Okay. 3 and negative 3 make our denominator 0. Correct. So that's where the vertical asymptotes would occur. Does there appear to be a horizontal one if we go way out to the edges, way out to the left and to the right? Mr. Dillavan, I believe it's pronounced. It'd be 1. Let's see. Let's roll this out way outside. Does my graph look like it approaches 1? It gets real close to 0. Correct, Jack. It's getting really close to 0. So how come we would have a horizontal asymptote of 0? Don't I just divide 5 over 1 again? That's my lead. How come we don't just divide the 5 over the 1 again to get 5? Jack?
Because the numerator and the denominator aren't the same degree.
Which one has a bigger degree?
The denominator.
Which one has a smaller degree?
The numerator.
Okay, so if the denominator's got a smaller degree, it looks... Okay, here's another function we're going to graph. This time we have 4x cubed plus 2 divided by the quantity x squared minus 9. And you guys have just graphed this in class. And, well, it doesn't look like there are any vertical asymptotes. Are there, Windsor? What do you have? Do you have any?
Doesn't look like it.
Doesn't look like it? But shouldn't there be a vertical asymptote at possibly 3?
Yeah.
Why would there have to be one at 3? What would that do to the denominator?
It would make it 0.
Okay, is 3 the only thing that would make the denominator 0?
Negative 3?
Negative 3 would also make it 0. So let's see what happens if we adjust this picture a little bit and we zoom out. It looks like, in a way, a cubic, but if I keep zooming out and I get this picture to expand and expand, we have new parts of the graph coming in. And if I zoom out far enough, what's our graph look like?
A line.
A line with what slope?
4x.
And it's got a slope of 4. Correct. It's linear looking with a slope of 4, and that has something to do with terms here. Anybody think they know why there might be a linear looking graph here with a slope of 4? Drew?
Okay. The numerator has a larger degree of 3, so you would divide 4x cubed by x squared.
Okay, let me write that while you're saying it. 4x cubed divided by x squared. What does that simplify into?
4x.
So the result of this graph is going to look a lot like the equation y equals 4x.
Correct.
Slope of 4. Okay, and that's definitely what we see. So based on the discussion we're having in class, here are a couple of items that should go in your notes. Example 3, we're going to look at again, looking at some of those properties from the previous page. So my rational function is this in green. And I'm going to start by comparing the degrees. The degree of the numerator is a 2, and the degree of the denominator is also a 2. So based on what we saw on the previous screen, is the top smaller than the bottom? It is not. So we're going to look at dividing these two. So I'm going to circle these right here. What would happen if I take x squared and divide it by x squared? What would I get? 1. So that will describe what we call the horizontal asymptote. Here's the graph. And it looks like as we go way out to the left, and I'm putting a dot here to indicate I'm moving way out to the left, my y values are going to approach 1. And if I go way out to the right on this graph, my y values are approaching 1 as well. So that takes care of horizontal asymptotes. Is there a vertical asymptote? Why is there not a vertical asymptote? That can't equal 0. Good. So far, going going back to here, we've taken care of horizontal and vertical asymptotes. Let's talk about intercepts, the bottom two boxes here. Y-intercept and x-intercept. The easier of the two is the y-intercept. How do I get a y-intercept? I'm going to substitute 0 in for x. If I substitute 0 in for x, what's 0 squared? Plus 2? 2 over 1. There's my y-intercept, which we can clearly see. So my y-intercept is found that way. Any x-intercepts are found by setting our numerator equal to 0 and solving. Well, how would I solve that? I could subtract 2 from both sides. And then I've got to take the square root of both sides. What's the problem? We can't take the square root of a negative without using imaginary numbers, so that tells us there are no real solutions here. And if we look at the graph, does my curve cross the x-axis? It does not, so that confirms that. Okay, example 4, the last one we're going to look at today in class. We're going to, again, do some of those same things. We're going to look at asymptotes, and we're going to look at intercepts. This is a rational function. Let's compare the degrees. What degree trip does the numerator have? 3. Denominator? 2. So, the numerator does not have a smaller degree. We have to think about dividing. So if I were to divide those, what would I get? X cubed over x squared. That gets us just x. Now, if I get just x, that's going to describe for me what we call the end behavior. So I've got a graph coming over here. Here's that exact graph. Well, if I zoom way out, that's the wrong way out. First of all, do there look like there are any vertical asymptotes? Where? Why would there be a pair of them at 3 and negative 3? Makes the denominator 0. If I zoom out even more and more and more and more and more and more, what's this starting to look like? A line with a slope of 1. Very nice. So my end behavior is going to look like a line with a slope of 1. And that's because we're comparing x cubed over x squared. Vertical asymptotes at 3 and negative 3. Let's move on to intercepts. How could I get the y-intercepts? We're going to plug 0 in for x. We can do that almost mentally. What's 0 cubed? And denominator is going to be 0 squared minus 9. 0. So that means, if we look at a graph here, it's going to cross the y-axis at 0, does it? It does that. Does it cross the x-axis at all? According to the graph, yeah. How would I find out algebraically where it does? Well, I'm going to set my numerator equal to 0 and solve that. How do I solve for x? I have to undo a cubing. But I have to do that then to both sides. So on the left side I get x. Can I do the cube root of 0? We can. It is 0, and that confirms here that's my x-intercept as well as the y-intercept.